welcome to the August 4th meeting of the Inventors, Southwest Missouri Inventors Network. We are in our 12th year of giving back one day a week to the Springfield community and surrounding area. Myself, Jan Helzer, and my husband, Galen Helzer, have found it to be rewarding to us in many ways because we learn so much from so many people in areas that is not our expertise. Through the years, we've had people come from so many different walks of life, different people that have won and lost in the invention area and the invention arenas. We have people that come from the manufacturing background, from the marketing background, from the sales background, and many people that say, oh, I thought of that, but I never put it on the shelf. I never took it to the next level. Well, at our meeting, we have people that have taken things to the next level, and we have people that have been on the television shows, and we've been able to, through here, and we acknowledge God as a great inventor. We've been able through here to see wins and losses and to help people on the invention journey. Today it is with great pleasure that I want to introduce my husband to you, Galen Helzer. He's owned Jag Engineering for 40 years, prototype model and foundry tooling. My husband for almost 45 years, and we have one son who we are very proud of. He's 38 years old. We have 2 granddaughters, and we have talked about filming our meetings, but we have not done that, and it's with Dr. Tom McLips that he is doing that today, so thank you, Dr. Tom, for doing that. And those of us that are here today, we look forward to some of the things that we're doing. We will be taking part in the Mini Makers Fair. We also are involved with Wellness for Warriors and presenting for veterans, first responders, firemen, policemen, and those that are in the arena, as Mr. Rogers says, watch the helpers. And so it is with that today, and with those of you that are here that have been supporting these meetings for 12 years. Sometimes we have 5, sometimes we have 15 to 17. Other times when we promote, we have 50. We like to get to know you. No idea is too little. What we do is we tell you that when you come to our meetings, that you never disclose the exact idea. We would need to sign a non-disclosure, non-compete, which at these meetings we don't do, so we ask you to talk in generalities and not do something that will hurt your invention down the road as you learn together with us or as we learn from you. So I want to tell you a little about my husband, Galen. And what I want you to know about him is that God has given him a brilliant mind, that he sees things in ways that I can't, as far as in dimensions that I don't understand. And he's going to today share with us some things on fairing that I have no idea what I'm going to learn, but I'm kind of excited about it when I saw him picking up things that I have no idea how he's going to teach us today. So Galen, thank you for doing this today, and have fun.
Well, it's going to be fun. Topic for the day is maybe a little deep for a shallow mind, maybe a little shallow for a deep mind, but I'd like to talk about geometry. That's something I have to deal with every day, and something I know that many of you have to deal with every day. Often you may not even know about it, but you still have to deal with it. I'm going to start this off with a little bit of some examples here. What's the difference? On the board it says orthogonal or organic. What is the difference? Does anybody know? Who can tell me? Orthogonal, its definition is
Wait, orthogonal, does that have something to do with the mouth?
Not your noggin, no, nothing to do with your noggin.
Ortho, doesn't that have to do with your mouth?
Has to do with the word normal.
Oh,
If you stand a pipe up in the middle of a table and it stays there and it is perpendicular to the face of the table, that is called normal. And a pipe in the middle of a table, I don't have.
like your straw in your.
Like a straw, only, you start getting something like this. You have to imagine this in 3D, but I'm representing it in 2D. You have a Z dimension, you have an X dimension, you have a Y dimension. You kind of get that by doing this, the left-hand rule, or the right-hand rule, whatever. I've seen machinists do it either way, but in the typical orthographic projection of geometry, everything is in relation to a world zero. It's either Z positive, Z negative, X positive, X negative, or Y positive, Y negative. That's orthogonal. This piece is just a pill bottle. This piece has parallel walls, it has a radius top, it has a radius bottom, there's a radius cut out of the bottom to give it a way to bear. It has a helical thread on it. It has a flat-walled cap and a flat top on it. I'm going to say that that part is an orthogonal design, okay? This, on the other hand, is a boss that is more of an organic design. And the real difference is in how one would describe either of those designs to a computer or to a system, a CAD or a CAM system. This would be very simple. That's a figure of revolution. Add to that the helical of the thread and the cross-form shape of the thread. This, how in the world, where are you going to start? It does have a flat bottom. It was ground off of there, but that's about where it ends. Where do you start? Well, that's called an organic design, and by the nature of the glass, this was pulled into shape, probably over some type of a buck or something. This glass was pulled, and there are marks from a plier where it was pulled. You can see those on the little flappies here.
Can you pass that around?
I can, and I will. It is glass, it will break. Drop it on the floor and we'll find out. But you see the tooth marks where they pulled it down and kinked it? Okay. A CAD man's worst nightmare. To have that thrown on his desk and say that needs to be documented by noon. It won't happen.
So if you're doing CAD, you can't just take a picture and it'll automatically throw the dimensions on from the picture?
Probably not. There's more to it than that. Quite a bit more to it than that. The word normal and orthogonal are really interchangeable. In Euclidean geometry, which is what most of us are used to using daily, orthogonal refers to perpendicularity, or being at a right angle, or being square with the world. Orthogonal thinking in a design, it's limited to points, lines, and arcs. And in past presentations I've made here, orthogonal thinking, points, lines, and arcs, CAD is simple as 1, 2, 3. Points are 1, lines are 2, arcs are 3. That's the way they sit in a database, in a CAD system. It's very simple, simplistic, many products. Even this product, this is just a pocket knife. Even this product is basically an orthogonal design. There are probably some curves, some splines, but those are probably radii, because that was cut on a CNC machine.
So say what orthogonal is again?
Orthogonal is square with the world in most of its features, square with the world. This marker, it's a figure of revolution, it's square with the world. It's something that's man-made. Orthogonal leans more toward things that are man-made. Organic leans understanding more toward things that are found in nature, as the petal of a flower.
Like the tulip in the bowl?
Yes, yes. There is nothing same, no sameness there. There's a possibility that there are three similarities there because it has three legs, but I doubt that there are perfect symmetry in three ways on that, because it was just pulled. Orthogonal thinking is limited to points, lines, and simple arcs. Organic thinking is unlimited by those criteria. Organics are complicated with splines and faces that are curved in more than one axis. Splines and faces.
Can you say that again?
Organics are complicated with splines and faces curved in more than one axis. Who knows what a spline is? What delineates a spline? Anybody? Where do you start?
Is that the backbone?
A spline? No, a spline is a geometric feature. What is the backbone of a spline? Where do you start with a spline?
It's round, it's a shaft, it has teeth.
There's always one of those in the crowd.
Did he hit it head on?
You know why that's called a spline? Usually because the shape of the repeat is not orthogonal. The repeat is orthogonal, but the shape of the volute of a gear or a spline is spline based. It really has no reasoning, no ordered structure that can be described. It has to be described with rotary action. It is not typically described with orthographic projection.
Those are big words.
Does anybody know what a sweep is? If you make a sweeping form, a sweep.
Does that have to do with arches?
An arch is a sweep, yes. Typically an arch is a sweep. A sweep is a form, and it is an orthographic form, an orthogonal form. A sweep is a cross section that is driven on a spline, or on a line, or on an arc, or on a combination of any. And that can be in 2D geometry or in 3D, but it's like a gutter or a pipe, or spaghetti is a typical of a sweep. It's all the same shape, no matter where it goes, where it lays.
Spaghetti after it's wet?
Absolutely. Absolutely. Describe spaghetti after it's wet and laying there still. Let it dry and harden there. You have a line down at center, and you have a circular cross section that follows that line everywhere that piece of spaghetti goes. And it doesn't change, mostly.
So it isn't an absolute then? Your last word was mostly, so it's not an absolute.
That's because there is no such thing as perfection. There is no perfect. In human description, whether it be organic or orthogonal, all we can do is approximate nature. We can't replicate nature in exactness. We can't replicate that bowl, but we can come close enough that your eye could not tell the difference. Does that answer your question?
Yeah.
Or your statement? We talked about a sweep. You understand a sweep. A loft is always organic. A loft is a mixing of two splines. Splines, let me tell you about splines. What is a spline? A spline Now, if you're gonna say that's a curve, okay? That curve can be described. That curve can be described two ways. One way is you can take tangencies off of this and you can have weighted points.
Probably ought to use black so that it picks up.
Okay, here's my spline. Okay, here's weighted points. And this will come here, and this will come here, and then there's gonna be one here, because I messed that up. But there's gonna be a point here, there's gonna be a point here, there's gonna be a point here. And the more you pull those points, the more influence. Now you can set the influence, or you can pull this. You can move its dimension, or you can move its effect, its strength. How hard does it pull? If this pulled tighter, if you set the pull of this tighter, this spline would be more like this. You get what I'm saying? It's each of these points influences the spline. This is a non-uniform relational Bezier spline.
Bezier?
Bezier, B-E-Z-I-E-R.
What is Bezier?
Well, he was an old Frenchman that invented that. They named it after him, and a system for describing organics. Pretty much the bulk of CAD software in its early days was figured out by French mathematicians. And we have them to thank. There's Dassault, there's Bezier, go to Wikipedia, there's about 50 mathematicians from France that have put this together over the years. There's another type of spline. This is called a B-spline that I just drew. There's another type of spline. Instead of a nerve, a relational, the relation is the relation of these pull points, okay? That's the relation. Okay, this is another way to describe a spline with points, and all points control that spline through the spline. From each of these points lie a vector with a length in the description. Each of these vectors, if this is a point, there's a vector. And the strength of that point, how it influences from here to here, from here to the next point, is by how long this vector is. This will have a strength vector out here, a strength vector this way. The length of that vector tells the influence of that point. And of course, its XYZ position, you can change that. In most CAD systems, you can change the position of the points and the strength and the angular direction of the influencing tangencies. What are you doing, Ken?
Trying to make it
Trying to get it set up so
building
that
something.
Dr. Tom's doing a good job. He's just trying to make it so he has something to set the camera on a
There you
little
go.
better.
A loft is a face. A loft is a face that is created by the intersection of two totally different splines. And their influence on the face becomes the surface that you see on that piece of glass. You've got splines one direction, you've got splines, the descriptive part of it, how you would describe that. Let's take this. Pass that on down. What kind of geometry is that? What kind of geometry is this?
It's a portrait.
What kind of geometry is that, Ken?
It's be orthogonal.
That is orthogonal. That would be that would that also be orthogonal, even though there's curve, it's spherical?
It's just nothing but curves. Arches.
If, and
Splines.
I say if that is a perfect sphere, that is basically a surface described by 2 points. The center point and a vector, a normal vector from the inside. All faces of that surface are the same distance from that center point. That would be considered an orthogonal creation there. What kind of creation is this? What kind of a design is this?
You need to hold them up each, Galen, so that we can photography them.
It's a little mag flashlight. Would that be considered an orthogonal or a organic?
Orthogonal.
Probably orthogonal. Okay. This is a little mouth thermometer. Would that be considered orthogonal or organic?
I'd say organic.
And why?
Because it's all different. There's curves.
Okay. There's a real good reason why. That's supposed to go under your tongue and you don't even want to feel it. You want it to just be smooth in and smooth out. And that's called fairing. How fair is it? How easy does it go in? The nose of a bullet, how easy does it go through the air, cut the air? You don't worry about when it hits because it's going all over the place when it hits. But the shape of it going through the air, that it has a boat tail or that it has whatever, splits the air in the front, whatever, however it leaves the air in the back. Think of that as a bullet, you know, that's going in under your tongue. You don't want to mess around with it under your tongue, you want to leave it there.
So having mercury doesn't have anything to do with it being
No,
organic?
the surface design is all we're talking about. We're talking about design. Orthogonal or organic in design. Okay? Here's a pair of earbuds, Apple earbuds. Now they are cylindrical, what hangs down, but the piece that goes in your ear, goodness. And there's a reason. And the reason is they gotta fit in everybody's ear. One set of earbuds gotta fit in everybody's ear. Everybody's ear is different. Well, you're gonna push and shove that until it seats in some way. You know, you don't want to make blisters. You don't want to bloody everybody's ear, or even half the population. You don't want to bloody half the population's ear. Nobody buy an iPhone. So the shape of that is highly refined, highly faired, highly smooth to do its job for the entire population. Got a few more goodies in here. Anybody know what that is?
Nose clamp.
That's a bull lead. Put a rope in that and you put that in a bull's nose and you can take him anywhere you want. But you don't want to bloody up the bull's nose. So look at the shape of that and tell me that the closer to nature we become, that goes in a bull's nose to do a job. The closer to nature you become, that's pretty close, you're getting into the bull's nose, that is more of an organic design. Hey Terry, how you doing? This is out of my cowboy collection. This is kind of a mix. This is a little fencing tool that goes over the horn of your saddle if you're a cowboy, and you can pull staples or hammer them in as you're riding the range. That's kind of a little antique restored tool.
Heavy duty.
I didn't grow up with one of those. I never saw one of those until I saw one on the internet, and I had to have one.
I've never seen them.
Well, a real cowboy would have hooked one of those over the saddle horn on his saddle. Unless he got totally bucked off, it'd stay there. But he was able to drive stables and to repair fence. And I'm sure there's a way with some of that to where you can stretch a fence or kink the wire to tighten the wire or something. There's a lot of things that farmers and ranchers do. Now this, first of all, there's a carabiner here. Let's talk about that carabiner. It kind of looks organic, doesn't it? But it really functions more orthogonal. Section, that's more of a, I would call that more of a sweep. The shape of that is more of a sweep, okay? This is a taillight for a bicyclist. Hang off of the back of his bicycle seat. And draw attention. I'm gonna say that that is totally, totally organic.
That's not what it looks like though.
It's rubber. If you lose it, you don't hurt it.
That tail light looks like it goes with the, bulb wires.
Yeah.
That's a possibility. That's a possibility.
That goes in the other end of the wall.
Okay, this came out of the shower this morning.
Man, I didn't know that.
This came out of the shower this morning. This actually came off the shelf.
That's what it's for.
Here's a bar of soap, and that bar of soap was made in a mold. And here's a little take home for everybody that doesn't know. If you buy soap, the soap companies are screwing us. They're making the soap and they're filling it with water, and when you go home with the soap in a box, it's got a lot of water in it. You take it out of the box and you start scrubbing with it, it'll just turn to mush in a heartbeat. Buy your soap out ahead. Buy 4 or 5 or 10 or 12 bars and put it on the shelf. Open the box, take it out of the box and let it dry out. This has been out for 3 or 4 months and it's pretty darn hard. That'll last a long time. It's dried out. It's tempered. They call that tempering soap.
So when you're crossing the desert, after 3 or 4 days, you can stop and say, man, I need to bathe.
There you go. There you go. Okay. What do you think? What do you think of the design of that piece of soap? There was a mold made, and there was chemicals and paraffins and whatever put into that mold to make that bar of soap. What do you think of the design of that bar of soap? You think that's orthographic, orthogonal, or do you think that's organic?
I think it's orthogonal.
I would tend to agree. There were simple dimensions. They make millions and millions of bars of soap. They didn't go to the trouble to use splines and make anything fancy, and then they engrave their name in it. So that's proof that there's a radius on there that they programmed and put their name in. Okay, this came out of my shower this morning. That's the same soap. Now, after it's been used, that's much more.
Last like forever.
That's much more organic because it's been handled,
Massage.
and massaged, and typically, I say typically, designs that are organic are not sharp anywhere. And my point with that sliver of soap is the sharp is where I've rubbed it sharp. The sharp on a plowshare is where it's been rubbed sharp. And nature does sharpen things of its own accord. The peak of a sand dune, where the wind blows the sand up in the shape of, an ocean wave, and then at a certain point it blows it over the top and stacks it on the other side. And the sand dunes roll, and they're never stable. All those sand dunes are organic shapes. They change readily, but there is a sharp point on them because of what they're made of. But I found that interesting. Look this little puppy over. That's just a pretty little bowl. And he's fairly smooth on the inside. I'm going to say that somebody really tried to make that, basically they really tried to make that orthogonal on the inside. And I'm not sure what they did to make the outside, but the outside is definitely organic. And it's something to do with the way it was made. Whatever material it was made of did not totally conform to a mold or whatever. It is laying right where it is, and that gave it the design after it was plated or whatever, gave it the design you see on the little bowl. But I'll leave these up here. We've talked about normal. Normal and orthogonal about the same. Normal is the best way to describe orthogonal. Normals are involved. Now to the topic of the day, fairing. If you ride a motorcycle, you know what a fairing is. Tell me what the fairing does. Somebody that rides a motorcycle, tell me what the fairing does.
Don't we have an inventor here that has been invented for all over the world for parts on a motorcycle?
What does a fairing do, Ronnie?
Well, for me, it turns the air the way you want it to turn it.
Does it give you better fuel mileage?
Hope so.
You hope so. Why would it do that?
It smooths out the airflow.
Exactly. It smooths out the airflow. Fairing, any design, streamlines it. A vehicle, a boat, an aircraft, or any organic face. And you fair something by adding fillers or smoothers. You either pull up a lower or you push down an upper. If something's sticking out too far, you blend that down. If something you got a kink down in, you bring that up. And that's called fairing.
Is that always with a hard surface, or can you do that with different types of plastic and?
It's much more difficult to do with a hard surface because soft surfaces typically fair themselves. Fabrics, flippers that you would wear in scuba diving, you know, they take on different angles as you use them. They pretty much fair themselves. And studying flexible designs can be a real interesting deal when you're doing geometry. This will flex, and how will it flex? Okay. Have you ever heard it bragged that it's a fully faired and race ready? You know, this motorcycle is fully faired. This boat is fully faired and race ready. Fairing a boat hull is a big thing. Naval architects design the hull of a boat. It has to cut through the water. It has to do certain jobs. It has to balance the boat. It has to provide stability, but it also has to flow through the water, and the water is a virtual solid. An airplane has to flow through air, which is not a solid, but it still responds similar to a solid. All the rules still apply. Fairing came from a Germanic, old High German word of fagar. Not heard that before. Another definition is the Old English, appealing to the senses. If you're fair, you're appealing to the senses. Or if you're doing the job of fairing, you're beautifying, or you're making to appear or become clean. A clean face or a clean surface won't disturb a flow around it. That's the hull of a boat, the hull of an airplane, the wing of a race car. you don't want the parachute until you pull the handle.
So how is it on the motorcycle?
Well, on a motorcycle, it's all a frontal thing, because you really have very little control over the air leaving the motorcycle, except on some of the drag bikes and the like. They'll have a fairing, or I've seen aerodyne things on the back of a street racer that you get down under the fairing and air flows up over and over the back fender. I've seen some fairing for aerodynamics. Is an interesting thing. When you cut through the air with an object, it doesn't really matter what the front of the vehicle looks like. It's the cross-sectional area. If you want to go faster aerodynamically with a vehicle, you have to reduce the cross-sectional area that you're pushing through the air. In other words, don't put bulbous baby moon hubcaps on your hot rod if you're going out to the salt flats. Put flat ones, because those bulbous ones give you a larger cross-section. Run smaller wheels. Run everything tighter. Run a smaller cross-section. You might as well take a brick and push it through the air. And what happens is, out in front of this brick stacks a bunch of still air. And the air splits itself. But there'll be a needle point, or it's more blunt. It looks like the front of an airplane. It's blunt, and air, even in the front of an airplane, air will stack up on the nose of the airplane, and it will split out. The molecules of air will split out ahead of the airplane in still air. What you can help in the design of aerodynamics is how the air leaves the vehicle. If you fair the air that leaves the vehicle so it doesn't come around and suck you and hold you back with vacuum, you make razor edges on the trail edge. The trail edge of a wing is a razor edge. You try to control the airflow so that it leaves undisturbed. You're going to disturb it going through it.
So let me ask
you want it to come back together and not hold you back.
Let me ask you this. We have an inventor here that has a product that is just now out on the market. Dr. Tom has a product that's called the rocket launcher. And can you relate what you just said to the arrow that comes out of the rocket launcher and how that works, Dr. Tom, with what Galen just said?
I can give you the concept. It was discovered many years back. It's actually what you're describing is called base bleed in projectile sciences.
Base bleed?
Yeah. So what's happening? What's happening in the background as your projectile's moving is you're creating a vacuum behind it, which actually slows you down. So if you can direct that air, or if you can put something with a little bit of pressure behind it to push that air, it eliminates that vacuum and improves your performance.
That's why you see the wing on the backside of a station wagon or on the backside of a race car. They're trying to control the air as it leaves the vehicle.
If you look at some of the older, or even on some of the modern military projectiles, when they're launched, there'll be a small burn going on while it's flying through the air, like off of a battleship, big projectile. That burn's not really giving it any boost. It's just taking care of the vacuum that's behind it and eliminating that.
It's compensating. It's a
Yes.
compensating burn that goes with it.
Yep.
Fairing means smooth, having a continuous, even surface without crease or wrinkle. Fairing, filling holes in low areas, reshaping voids, or grinding down bumps so they blend in with the surrounding surface, appearing level or fair to the eye, to the touch, or to whatever water or air that it's going to see. Fairing small gouges and dents in whatever material, wood, fiberglass, aluminum, steel, say the hull of a boat, would be done before you primer and paint it. So it's a finishing operation. If you don't take care of the fairing in the design, you need to take care of the fairing by adding and subtracting after you've produced the product. So when is it a better time to fair the product really in the design, if at all possible, rather than after you've built it. After
Is
you grind
that
it
what
down.
you saw with the rocket launcher? What did you learn with what he just said?
So in the design of rocket buoy itself, right now the tail, you'll notice, is flat. So we still got some performance issues we're working on, but we have a whole different tail design that is going to be compensating for that. I can't really get into the details of it, but we've actually taken some 1950s rocket propulsion ideas, modified them, and we've built the prototype already. We just got to go out and start testing it to help eliminate that problem. So actually this will be the second prototype. We did the first prototype last summer, and we actually seen a significant performance improvement. And we'll see how this goes. We made a better prototype, and it'll be a while before we're ready to fully release it because we're making some other little changes along with it. Changing that tail end can have a very significant difference on your performance.
That's why on cars, they call it a spoiler
Mhm.
in the back, because it breaks that vacuum.
Yep.
Fairing a design makes it functionally significant and pleasing to the eye. Sexy cells. We got lovers here. It's a little statuette. That initially was probably done in clay and daubed up, and you can see that it really wasn't too well faired. You look at it closely, you can kind of pass that around. You look at it closely and you can still see the daub marks. It's smoothed over, and that's probably one of 10,000 replicas that have been made of resin of that design. But there are flaws in it. When you compare that to what you would see as in a photograph in a magazine of the exact same thing, you can tell the organics of perfection of a real couple is much, much different than we see in the image. So when you have an image, an organic image, usually it's less than the real thing. A fair design will always perform more satisfactory than a ganged up mess, you know?
Well, could you think of that as a ganged up mess with all the lines and all the splines and it's not just a piece of spaghetti, there's spaghetti going like, kinda like atoms, you know?
You mean in the example of the lovers here?
Yeah,
Okay, well, is that pleasing to your eye? Maybe from a distance, maybe the subject matter, but it's pretty crude.
can you get a close-up for the people that we're showing this to?
Set that there, you can see the incongruities of the design will become very apparent the closer you come up to it. One of the properties of a well-faired design is it will drain and dry properly. In the big picture, liquid will sheet off of it ready, as will gases. Both of those, of course, less their frictional suction to the said face. That's why a golf ball has dimples.
Now say that again?
You wonder why a golf ball has dimples. Does anybody know why a golf ball has dimples?
Goes through
Air
the
flow.
faster.
Pardon me?
It goes through the air faster.
And what's happening there? Why? What is happening?
Causes something. I don't know what it was.
It has to do with a laminar, and it's hard to say with my crippled tongue, a laminar surface.
Yeah. Keeps the air from sticking to it.
When I blow air, this is air forces, okay, against a golf ball. The air on the face of this golf ball sticks. It sticks on that golf ball. It won't move. The friction holds it and locks it there. And it unlocks and releases erratically. It doesn't really do that in an organized fashion. And so the golf ball will have an erratic path if it has the dimples we have dimples in a golf ball. A laminar flow of air, this air that's going through, it's all broken up and it's organized in an organized structure because those dimples are an even amount apart. And therefore, it will go faster and farther in a more organized direction without anomalies. Even if it's spinning, it doesn't matter if it's got English on it, if it's spinning or if it's just going still through the air, you still have the advantage of organized laminar flow releasing of the vacuum of the air that's stuck to the face of a golf ball.
It's a
So,
coating of air around it, really. And
You're breaking up the coating of air. With the dimples, you're breaking up the coating of air around it. I didn't bring the picture. I have a picture of an intake manifold for a race car that they've cut dimples in. And court's still out on if it does any good. It was an awful lot of work, I gotta say that. Whoever did it, it was an awful lot of work to go in and do it evenly. And they did it evenly.
this fluid flow is true for any type of fluid, not just air.
Yes, not just air, water, any type of fluid.
This
Any type of
this
fluid.
equates to, in the fire service, we call it friction loss in our hoses,
Yes.
because you have a turbulent water flow going on closer to the edges.
Yes.
So actually the water out toward the edge of the hose
Never
is
moves.
moving slower
It
than
never
what's
moves.
in the center.
Yeah, it never moves. Actually, what's stuck to the wall, the water that's stuck to the wall, the inside wall of the hose, stays there until the job's done.
Yeah. And same problem in rocket buoy, coming out of the barrel, we deal with that there, even in that short distance, you have problems with your flow.
With the rocket buoy.
Yeah, because there's that friction loss along that barrel as that air is pushing that out.
Golf balls have more or less dimples, they'll go shorter or further distance also.
I have heard, and there are regulations now. There are regulations on this side of the Atlantic Ocean for how golf balls are to be for regulation play. There are different regulations on the other side of the Atlantic. I don't know if they play golf across the Pacific, but I know that the English and the Americans have totally different golf balls. And it's in the shape and size of the dimples on the golf ball. And some people can quote you what that is. I'm more into the function rather than the fact of the device. You may say the rounded thing is boring. Turn it as you may, it remains round and pretty. Some love edges, sharp lines, and flaws. Give me those rounded, boring things, those fared asses. They satisfy like no other. Beauty is in the blend and the osculation of them. Now, there was a new word, osculation. How many people know what that means? Anybody? Jan, it's not fair. You had me.
You live longer.
What is osculation? This is osculation. This statue depicts osculation. Osculation is kissing tangency, often in 3 places minimum. Kissing tangency. That represents a curve, a spline. It's controlled by points, whatever. The more control points, the more chance for kinking a spline. If you're messing with splines, the less points, the better. I'll get on to that in a little bit. Osculation, there's a point, and that's not a very good circle. every point along a curve, there is a place that you can pick 3 points of tangency. I'm not very good at drawing a circle, but as that moves around, its diameter will move in and out. But you can form fit a spline with an arc. If you can't, it's not a spline. That's kind of a bold statement. Osculation is a kissing tangency by 3 points. Those 3 tangency describe best arc fitting at a beginning point, a midpoint, and an end point. All curves can be approximated by a set of tangent arcs. Most software has that capability. If you give it a spline and you want to simplify the spline for production in some type of a CNC machine, you can explode it into tangent arcs, a set of tangent arcs. And you would give it a tolerance of deviation that you want it to hold to, and the software will do that. Now, let's talk about something else. You guys got that osculation is the point of tangency? That can happen in 3D, but it has to happen on 3 points. A sphere will fit into any 3D surface. The right diameter sphere will fit anywhere on that and touch by 3 points. It's the nature of the beast. I keep losing my place here. What's a point of inflection? A spline or a curve comes this way, and what happens when it turns? Okay?
It inflects.
This osculation, see, we'll start over here, and there's a circle that will fit this. There's a circle that will fit this. Okay? But at some point here, we have a circle on this side, okay, that fits this. Somewhere between here and here, there's an inflection point. I'm going to just say right there it is, okay? The inflection point is where an osculating circle becomes of 0 diameter on one side and of infinite diameter on the other side. Think about that a minute. Think about what that does to a computer. As a computer tries to swallow that point of inflection, it'll choke on that, because a computer cannot do infinity, a computer cannot do 0. It can't calculate 0. When it comes to the point of inflection, a computer's in trouble, because it doesn't understand nothing, it doesn't understand infinity. And I'm going to say that probably we humans don't understand 0, nothing, to not exist, nor do we understand the infinity that God could teach us.
So basically, it's cause and effect beyond how we actually see things initially.
But computers do calculate splines. They do calculate osculating arcs and curves. They do. How do they do that? They write an algorithm that compensates or overlooks the exactness of that point. And they replace it with a little short line with a length that's set at a value that's balanced within the tolerated error. They just ignore it. And it's so small that you don't know it. But the computer can deal with that. That's a line that goes from here. It's not even an arc. It's nothing to do with, it's just a line from this point to that point.
So it's not a point, it's an actual line.
Yes. Yes. It changes. It's not arcs anymore. There's a line in there, a microscopic length line, And the software just jumps over that, doesn't try to calculate what diameter circle that would be, because it's a 0 diameter circle on one side and it's an infinite diameter circle on the other side. So it just replaces that little, it sees it coming. Computer, as it calculates, it will see it coming, and it'll replace that for a certain length with a straight line. When you're playing with splines, curves, when you're playing with them, and we do all the time, if we have a spline-based project, take a perfect arc. There's a center point. Okay. There's a center point down here. Okay, that arc has the same amount of curvature anywhere on it. And would I be correct on that? There's no change in curvature on a true arc. Okay? When we're looking to fair something or smooth something, most of the software out there, not just what I run, but most everyone's software will allow you to put curvature cones. It'd be better if that was a different color. And the computer does this in a heartbeat for you. Those are all supposed to be the same length. Okay? They are all normal to their position on the curve, and they all would be the same length, showing that that particular curve is actually an arc. Okay? What if the curve is not an arc? Where'd my black marker go? Here it is. What if the curve is not an arc? Okay? You see a difference in curvature. How much curvature? Well, it's going to look something like this.
So if you were to put an arc up beside that, can you show the difference between a curve and an arc?
You see how the curvature cone gets bigger, the more curvature is on it, and it gets shorter, the less curvature is on it.
And so if that was an arc, what would be the difference?
It'd all be the same if it were an arc. It's not an arc. The curvature cone does not show that it's the same amount of curvature. All these do, these vectors.
I don't get what then, how one is an arc and one is a.
This is a curve.
So an arc is not a curve?
An arc can be a curve. An arc is a type of curve. But it has some very distinct constraints and rules.
Center point.
It has a center point. This has many, many, many center points. As you osculate circles to fit in this thing, the center points are going to move. The diameters are going to move, thereby the center points are going to move, right? Am I right on that?
Correct.
So an arc would be a more perfect curve, where this is curved a little, straight a little, curved a little, straight a little kind of thing.
Or
here.
whatever.
Yeah.
Or whatever. Okay. Changing length on the comb shows acceleration or deceleration of curvature. Now, what if you have a curve that looks like this? What will the curvature comb look like on that? It's going to be, I'll get the red one. The curvature comb is going to be,
Same as last one.
it's going to get shorter and shorter at this point, and then at some point it's going to,
So why did
at the
it
point of
cross
inflection,
over?
it jumps sides.
Why did it jump sides?
Because there was a point of inflection. Because the normal is pointing toward the center point of the osculating circle. And it looks to each side of that point, and that normal vector, it looks to each side to decide how long the next one is going to be. The more curvature, the longer the line is. That's just a computer algorithm. Usually it's adjustable. What we use these for is we're trying to straighten out, say we've scanned something and we've taken a spline off of it, and we come along and we've turned on these curvature combs and we see, well, right here, there's a place where that jumps sides. Well, there's an inflection point there. That means there's a kink. That inflection point means that it changed, and you'll see that. So we drag that around. We can drag the control points on this. Either we'll smooth it out. It's interesting to watch because on a computer, as you drag that spline, you'll see these combs move as well. It recalculates that very quickly, and you can feather out, you can fair a design just by pulling it around. This is my representation here of coming here and then coming through the inflection point and coming out here. You kind of get the idea.
So that's basically what's happening on your levers. Over and over and over again.
In 3D.
In 3D.
Yeah, they're not very smooth.
Over and over again.
Over and over again, yeah. Okay. You see this though, that's fairly smooth. When the curvature comb comes, that's fairly smooth. But say you have something that looks more like this. So your curvature comb ends up looking like this. Okay.
Good so far. Well, actually, let me go take a quick break in the bathroom.
You have a point of inflection there.
This is okay, it's doing something.
Okay, and these are very minor distances we're talking about here when you see this. We have a point of inflection, but then we've got a rise here. We've got a hump in this spline, and we may not see it in the spline, but there's a hump there because the curvature comb is up. So we need to take this point, we need to move it down and smooth that down to where that's smooth there, if it's necessary to have this particular geometry. And then we have a point here that it's got a low place in it, okay? We need to smooth that out by allowing the spline to feather more this way, and that will allow this to be more smooth. You're looking for smoothness in the curvature comb, which is an amplification of the detail of the spline. And when you're looking at it in 2D, it's very difficult to see, but when you put the curvature comb on it, you can adjust it. You turn that into a 3D item, and you look at the light shining across it, and all of these inflection points, high points, low points, you can see those. They'll just glare at you. You'll be wet sanding for a long time to take them out of it. And typically fairing, wet sanding is how we get, on a car, you're bondoing in, you're fixing damage on a car. You want to put a black paint job on, you want to see a reflection that is even and consistent across the whole panel of the car. You're going to wet sand that, and you're going to watch the light as it reflects off of that face. And you're going to do it over and over and over, looking for smoothness, for fairing. Turn this right side up, I'll get back to my notes. Fairing or removing of kinks, it can take a lot of time. Anybody ever wet sand a car? You know what I'm talking about. You spend a lot of time. Anybody ever use over and over different colors of telltale primer paints? You paint one color and you paint another, and you see when you go through it, you've gone too far, and you're looking for smoothness. Visual acceptability and smoothness. That's shape and scrape. That's bond on. That's smoothing it up. If you do that digitally in a product, and you smooth up the product in the design, you end up with closer to perfection, closer to organic.
So as you take the words and what you've shown us, what, if you were to put today what you've shown us in a sentence to take home with us, what three things would you say will help us with our inventions?
Well, that was my final paragraph, Jen, and I'm not ready for it quite yet.
Okay.
I still got some time. There are other ways to smooth the curve, automated ways, and this is in a CAD system. One of the easier ways is to simplify the data set. Use less points, less influence. The curve will smooth out the less influence you have on it. And today we have laser scanners. And you shine a laser and it repeats, bounces back to a receiver, and it gives you billions of points, billions and billions of points, a database that's megabytes, gigabytes long. That gives you a point cloud of a surface. But if you try to use all of those points, you're going to end up with a kinked up mess, because there's always outliers. There's always ones that came too high or too low, or, you know, it is not a perfect science. It'll look like the outside of that bowl if you try to take too much data into your model. So you take 1 billion points, and points to build a spline. 4 points will control what you want and give you the ultimate of smoothness. It may 6, 8, 12, depending on how long it is and what shape, what's happening. But the less points, the smoother it is. And most software has the ability to, they call it simplify, to simplify a curve. It shows you the present curve, and it will show you, when you simplify the curve, it'll show you an overlay of the coming curve. If you throw away, you got 38 points and you throw away half of them, you've got 17, 18 points, and you throw away a part of them, okay, you may have 9 points, and it will show you, as you click it and simplify it, it'll show you what your result is. If you're just looking for smoothness, you can go down to 2 points. At 2 points, you just got a line. Remember the 1, 2, 3? At 2 points, you just got a line. At 3 points, you got something, depending on, you know, the distance between the 3 points. But you can smooth up a curve by simplifying the data set. Out of billions of points, only a handful are necessary to replicate a beautiful organic curved face. Another way to fair a curve is to relax the influence that each control point has on the curve. And a relaxed curve usually only has a couple of steps. You can relax it 1 step, you relax it the 2nd step, it may still be close. You relax it the 3rd step, and it starts getting it's not what you started out with. Doesn't even look like what you started out with. But by relaxing, you're relaxing the influence that the points have in pulling that curve into the shape it is. And a more relaxed point set will give you a much smoother curve. In solid modeling and computer-aided design, boundary representation, it's often abbreviated as BREP, B-R-E-P, is used. It's a method for representing shapes using the limits of the face. A solid is represented as a collection of connected surface elements. And those surface elements are what we've been talking about in 3D, made of splines, surface elements. It's a collection of those. A solid model, this is a solid model. Could be described as a solid model if I cared to do it. I could scan that, I could take enough points off of that, and I could create splines to create that, a solid model of that. What I'm looking for in the end, I couldn't find it on the internet. I need all of those faces to be perfectly watertight. In other words, there's no gaps, no laps, it will hold water. When you're creating faces and doing it that way, it's real hard to do. It's easier to use Booleans and subtract a piece out or add a piece in.
What's the Booleans?
A Boolean is a very basic, this is a Boolean. A sphere is a Boolean. An extrude is you know, a rotation, a figure revolution, that's a Boolean. And it's the subtraction or the addition of that from whatever you're working on. Sometimes we have to drown. I'll get a model that I can't figure out, like the corner of the eye. I did a job, if Rob was here, it was his job, on his little crayfish. In the corner of the eye of his crayfish, in the mold, in the geometry, I did not create that geometry, somebody else did. There was an anomaly in the corners of the eye. The eye was a little football-shaped face. The thing just blew up. It would not create toolpath over the corners of that eye. It would not do it. I had to go recreate that, and what I'm going to say that I did, I drowned the problem. I took the corner of that eye and I made, I think it was a 3 thou diameter Boolean extrude that the tool wouldn't even see. It was what the problem was is it was a singularity. You have to describe a face or a surface with 4 sides, a set of U and a set of V sides. It makes a mesh. It's a quadratic equation. There's 4 sides, and you either have to lie to it at the corners, you have to do something at the corner. You can't have a singularity at the corners, or the computer it doesn't do 0. It won't do it. Or it goes off on its own path, and 3 days later it's still on that path. And it may still be thinking about it, but you're not getting anywhere. Keep it smooth. Solid is represented as a collection of connected surface elements, the boundary between solid and non-solid. If this were to be all faced up and be a solid model, each of these faces have telltales, or I'm going to call them surface arrows, and they point either inward or outward. The software cares, different software points them inward, some points it outward, but it's a telltale. They'll all be the same direction. They'll all either be out or they'll all either be in. And at the company that made the software, at their discretion, those arrows differentiate matter from antimatter, something from nothing. And that's kind of the coolest thing on earth for creating things, for creating designs, is to be able to differentiate something from nothing. and it's done in B-rep, boundary representation. In the end, energy spent on finishing a thing is always time well spent. This finishing or fairing happens in design, in production, in packaging, and in marketing. Can anybody tell me how finishing or fairing would be done in marketing? Smoothing up the deal, making it palatable, making it sexy. That's marketing. That's fairing the job. In packaging, you don't want the package, somebody picks it up and it pokes them in the hand. You don't want the package to injure somebody. You want the package to be smooth. You want it to have a finished feel to it. This is a pill bottle. The pills may have been the bitterest things on earth, but the bottle is slick and smooth. That's a package. The package appealed more than the pills did. How about in production? How can you smooth production? When you're making something, whether it's in a press and you're pounding parts out of solid plate or whatever, how do you finish that? You want it to be pressed out as burr-free as possible. So there's no need downstream to deburr it, to grind the ugly off of it, to make it acceptable. The more we have, we call it fine blanking. They make gears fine blanking. Well, that's a stamped out and it's done in one hit. Fine blanking is just another flavor of shearing apart out of a piece of plate or material, but the die has less clearance in it and it shaves the part as it breaks. It's called fine blanking. And coarse blanking is where you just take a punch and you just shove it through and whatever breaks out, and that's what you get. So finishing and fairing can happen in all different aspects. It's even profitable to consider fairing or finishing in logistics. If you're going to put a product on a truck, and the truck's going to drive all over creation before it goes to the customer that's just down the road. Logistics is the closest path from the shipper to the destination. That's fairing. And there's people that do that for a living. There's software that UPS, they try to make the route the shortest route for the guy's got to deliver to all the neighbors all around. Well, what's the shortest route to get there? They try to replicate that in software. Fairing or finishing in disassembly. When you're done with the product and you tear it apart, or you have to take it apart to service it. You have to reach your arms down in past a hot manifold and you burn yourself. That wasn't very well thought out. That wasn't very fair. That's actually unfair, but it happens all the time. Nobody really thought about having to take it apart, having to get a wrench in there to loosen the bolts. They put the bolts in before they put all the rest of it together. But to get the water pump out of some things, it's a nightmare. You have to take all the rest of it apart just to get there. They don't think about smooth disassembly, the quickest way, the easiest way.
I see your people here smiling.
It's a reference to auto engineers. What's the fastest way to get it together? Not thinking about how you're going to have to take it apart.
Yes, yes. I want to talk about a little bit in history. Anybody know the name of the company that made the P-51 Mustang?
North American Aviation.
Good, you're going to help me with this. NAA made the P-51 Mustang. They did that in 1940.
Was that a Howard Hughes thing?
Nope. I don't have the man's name here, but the first contract for the P-51 Mustang was for the British. The British needed airplanes, They couldn't buy them anywhere, and they came wanting a Curtiss P-40, but North American Aviation didn't make the P-40, and they said, hey, we got this idea for this plane. If you'll let us do this, we'll make these planes, and we'll beat the delivery schedule that it would take to make the design of the Curtiss P-40. We'll beat that timeline, and we'll beat that price with our design. The P-51, from beginning to the rollout of the first prototype airframe on September 9, 1940, wasn't my birthday, but that's the day. It was 102 days. Now, we were a country at war, and everybody locked in step with that.
We were not at war yet.
No, not yet.
Not yet?
1941.
Okay, so it was a business deal.
No, wait. I think it was a war with Germany, but I'm not really sure.
September 1940.
We was at war with Germany when the Jets bombed Pearl Harbor. I 100% guarantee it.
Yeah.
Now, what the time frame is, I really do not know. America was at war with Germany before the Jets bombed Pearl Harbor on December 7th, 1941. I guarantee it.
Regardless of that fact, whether we were officially at war or not, we were making guns and bombs and planes, and we were at war, brothers. We were at war. We were making things to bomb the Germans, we were at war. Our industry was capitalizing on the war. And as industry does, war is good because you blow stuff up. But they did that in 102 days. And it was a beautiful airplane, and it still is, those few that are left. One of the stipulations that it shoot four 303 caliber machine guns, same that was used in the Tomahawk. They wanted it to cost no more than $40,000, and they wanted to have delivery of the first production aircraft by January of 1941.
Yeah.
So in March of 1940, 320 aircraft were ordered by the British. I'm just kind of giving you the highlights of this.
Ken, what'd you find out?
You know, Liberty ship built in 4 days, 15 hours, and 29 minutes.
That's pretty cool. You build a boat.
They had a fatal flaw.
Well, I understand.
P-51 Mustang as a prototype they called it an NA-73X, which I did not know that. It was designed by a team led by lead engineer Edgar Schmud. They followed the best conventional practice of the era, but they included several new features. One was a wing design using laminar flow airfoils, which were developed cooperative by North American Aviation and the National Advisory Committee of Aeronautics, or NACA. NACA later became NASA. But the NACA left their mark on the little funky funnel looking ducts that you see in race cars, a knock-a duck. Was one of their designs, and I've studied into that. That's another whole meeting. This airfoil generated low drag at high speeds. During the development of the NA-73X, a wind tunnel test of two wings, one using the NACA 5-digit airfoils and the other using the new NACA 45-100 airfoils, was performed in the University of Washington Kirsten Wind Tunnel. The result of this test showed the superiority of the wing design of the NACA 45-100 airfoils. Another of the features was a new cooling arrangement. It was positioned rearward. It was a single ducted water and oil radiator assembly that reduced the cooling drag. I believe that's this little snout on the belly. The intake for the cooling was on the belly, kind of one of the things that made the plane look like it did. Later, after much development, they discovered that the cooling assembly could take advantage of the Meredith effect, in which heated air exited the radiator with a slight amount of jet thrust. Because North American Aviation lacked a suitable wind tunnel to test this feature, it used the GAL CIT 3-meter or 10-foot wind tunnel at the California Institute of Technology. This led to some controversy over whether the Mustang's cooling system aerodynamics were developed by a North American Aviation engineer or by Curtiss, although NAA had purchased the complete set of P40 and XP46 wind tunnel data and flight test reports for $56,000. We bought it and paid for it, so who does it belong to now? The ones that put up the money. The NA-73X was also one of the first aircraft to have a fuselage lofted mathematically using conic sections. This resulted in smooth, low-drag surfaces. To aid production, the airframe was divided into 5 main sections: forward, center, rear fuselage, and 2 wing halves, all of which were fitted with wiring and piping before being joined. And if I recall somewhere else, that 5 sections is how we still build airplanes today. It's the first airplane that was not a shape and scrape airplane. Its surfaces are not organic, not shape and scrape. B-51's entire surfaces are orthographic. They're conic sections, they're radiuses, they're fillets. They rolled it out 102 days after order had been placed. They didn't get their 303, they got a 30 cal cannon on it, but it also had 250 cal cannons on it. They were mounted under the engine, fired through the propeller arc using gun synchronized gear, so they didn't shoot the prop off of it. I remember when I was just a little boy, somebody told me that, and I thought, how cool is that? You don't have to have the guns out on the wings to miss the prop. You just shoot right through it, but you time it so that it doesn't.
Yeah, it was a pretty fast airplane too.
Yeah, that was World War I, wasn't it, when they invented that, to time the gun?
Now, the later models of the B-51 had 350 cal machine guns in each wing. And that's actually where the origin of the term, the whole 9 yards, came from. Because each of those machine guns had
9 yards of bullets.
Half-length ammunition.
Of bullets, yeah.
Cartridges.
Yeah. Well, I got another interesting little twist of history here that I found out in researching for this. Dassault Systems are the authors of CATIA. They are also today the authors of SolidWorks, which is the software I use. A Frenchman named Bloch, B-L-O-C-H, Bloch. He worked for the French Aeronautics Research Laboratory during World War I. And he invented what today we call the aircraft propeller. The mathematics to design and produce aircraft propeller were by Mr. Bloch. In 1928, Bloch founded the Society of Avions. His name was Marcel Bloch, and he had an aircraft company by that name. In 1935, he and another guy entered into an agreement to buy a company that made airplanes. They merged, and then came World War II. During the occupation of France by Nazi Germany during World War II, France's aviation industry was virtually disbanded. Other than the compulsory manufacturing, assembling, and servicing of German designs, In October 1940, Bloch refused to collaborate with the German occupiers at Bow d'Or Aeronautic and was imprisoned by the Vichy government. The Vichy government was the German-controlled French government, basically, as I recall. In 1944, the Nazis deported Bloch to the Buchenwald concentration camp as punishment for refusing to cooperate with their regime. He was tortured and beaten and held in solitary confinement. In the meantime, his wife was interned near Paris. Bloch was detained at Buchenwald until it was liberated on April 11, 1945. By the time of his return to Paris, he was crippled to such an extent that he could barely walk. He was advised by his doctors to settle his affairs because they didn't expect him to recover. After the war, he changed his name from Bloch to Dassault, D-A-S-S-A-U-L-T, and in 1949, he made that name permanent. Dassault was the name in trade used by his brother, General Darius Paul Bloch, when he served in the French resistance. It is derived from French for battle tank. Dassault acquired many aviation companies before he died. But he invented the propeller. How cool is that? I rest my case. Make it fair. Make it smooth. Think about smoothing out as many operations as you can. Whatever you're building, whatever you're doing, make it smooth.
We
I'm
learned
done.
about fairing today.
I'm done.
I didn't know those big words, excepting that I know when Galen kisses me, there's some sort of oscillation.
Osculation, not oscillation. There's no vibration in osculation. There is in oscillation.
Big words, and we are going to wrap this part up, but we have a business meeting, so we'll go ahead now and turn off that part of our meeting.